Hello and welcome to our first day of our buffers note packet. Please have your Ka/Kb chart out. We will be using that today. I'll probably split this lecture into two, so the videos are not really long. So we are going to be talking about buffer systems, and the first thing we'll do is go over what is a buffer system. So a buffer system is a solution containing a conjugate acid base pair with both the acid and base in reasonably similar concentrations. And these are pretty common, especially in our bodies. Our blood is a buffer system. And the reason they're important is a buffer system allows acids or bases to be added to a chemical system without large changes in pH. And it relies on something called the common ion effect. So a common ion means that whenever an H or an OH is donated or accepted, that something in there is going to be added that has a similar or the same ion as what is left over as the conjugate acid or conjugate base. So when a solution of a weak electrolyte, which would be an ion, is altered by adding one of its ions from another source, ionization is suppressed. And we'll look at this when we look at the most common types of buffers. So we're going to have two of them. The first one is a weak acid plus a soluble salt that contains the same ion that's in the acid. So an example of that is acetic acid, which we are all familiar with, plus sodium acetate. So acetic acid is HC2H3O2, and sodium acetate is NaC2H3O2. They both have a common ion. So in order for something to be classified as a buffer, one, it has to be a weak acid or base, which acetic acid is. They have to share a common ion, which these two do, and their concentrations, when given, have to be close to one another. So if you have one that's like 1.5 molar and one that's 0.5 molar, that isn't really that close. If one's 0.1 and one's 0.2, that's reasonably close. So use your judgment with that. It'll be obvious in any kind of questions. So to explain what's going on here, I'm going to write out the equations for both of these. So NaC2H3O2 is completely soluble. So if we put this in water, it breaks down into its two ions, just like we did when we did net ionic equations. It's the same thing. But we also have an equilibrium system happening with the acetic acid. So when it mixes with water, it doesn't have a straight arrow, it has a double arrow for equilibrium. And we know that this partially ionizes, so we get some H3O plus and some C2H3O2 minus from this. Right here is our common ion. So we have to go back to Le Chatelier's principle. Clear back from about October and November. It says when you add something, the equilibrium can shift to get rid of it. So if we have this equilibrium system right here and we dump in some sodium acetate and it ionizes, that means that we're going to increase the amount of C2H3O2 in this equilibrium system. So the high concentration of acetate causes equilibrium to shift left, which then causes a decrease in the concentration of H3O+, and the pH increases slightly. So in the next video, we're going to look at an example problem using our old method, and then we're going to derive a new method to be able to calculate this a lot easier. Stay tuned for the next video.